Good morning. So let's start the next lecture, continuing the series of lectures of Making a Habitable Planet by Professor Bergin.
All right. So today I'm going to talk a lot about what we observationally know about chemistry in planet-forming disks. And if I were to give this talk 5 years from now or 10 years from now, it would be probably completely different because the Atacama array has been operating for about 3 years now. Still not at its full capabilities, but it's getting there. And I expect the data flow will substantially increase, and this array, before this, the best resolution we would have was about 30 AU. That is, everything inside of 30 AU was in 1 pixel in our telescope beam, right? So now with the Atacama array, we can get AU scale resolution. So if you want to study planet formation, this will be the way to do it. But there's some things we know now that came from some really nice work from the arrays preceding ALMA, and then we actually have some ALMA data that are giving us hints of really neat results to come. And then tomorrow I'm going to try and make an Earth, and as you'll find out, is I'll be able to do it, but I'll also be able to not do it. So I ended up with protostars. So this is what we know about why do we care about the protostars again? This is the material that is collapsing and is provided to the disk. It's providing a sample that both the prestellar phase and the protostar phase are the initial chemical conditions of the disk. Okay, so that's how the disk starts. And it may be the case that where the relative disposition of these volatiles are may lead to different outcomes, right? So what we know is that half of the carbon is in some sort of solid form in the interstellar medium, and the rest of the carbon is in CO. A fraction, a tiny fraction of the carbon is in the organics that we see, all right? And we believe that these organics, along with the water, formed in the earlier phases when it was colder because they have deuterium enrichments, but there might be some additional processing when the protostar is born and the gas warms up. Now what's happening there is that the grains are 10K, and at 10K the hydrogen atom can zoom around, but heavier species can't, oxygen atoms or anything like that. But when you get to 15K or 20K, all of a sudden other things become activated on the surface. And what that means is different pathways, different chemical pathways are now available when this happens. And so modern models account for this possibility. Our best data are towards sources that are significantly more massive than our sun. 5, 10 solar mass stars forming. There are a handful of low mass stars where we see rich organic chemistry, but it's just a size scale effect. That is, massive stars release more energy, so have a bigger region where the ices are evaporated. Hence, our less powerful telescopes see that better. Low mass stars like our sun have a much smaller region where the ices will be evaporated. So with ALMA, we're going to solve that. And then they have deuterium fractionation, the cold phase. All right, now, Jack, I think David, and today myself at one point mentioned different flavors of stars, and so this is for any biologists who are here, just to give you background. So our sun is an average star. We call that a G star. That's based upon its temperature. So our sun's here. Stars less massive than our sun, we classify via spectral types. So a K star or an M star, these would be a half a solar mass or a third of a solar mass. They're less luminous. They have less energy coming out. And then stars more massive than our sun are F, A, B, and O stars. They go up to, let's see, there are 3 solar masses, about an A, maybe 2, 6 is a B, and the beasts, the 30 solar mass stars, are O stars. So just for context, you know, if we slip into spectral type, the ones that generally come out, M stars, are the most common stars in the galaxy. They're the lowest mass, so they're lower mass stars than our sun. So that will be something that I'm sure will come up elsewhere. Now, all right, the ISM chemistry we know is dominated by the formation of water, CO, and probably N2. N2 is homonuclear. It's hard to observe, so we have to get it by proxies. We think it's there. And then organic. So this is what's happening during the disk, and we know the deuterium enrichments are there. So what happens next? So there's sort of 2 viewpoints on this. That is, the formation of the disk is very violent. Everything evaporates and then re-solidifies. And in that sense, it's completely reset. All right, so the disk formation is a very violent stage. Now, the meteoritic inventory that the chemistry, the Lewis chemistry that we've been talking about, all 3 of us actually, implies that is based upon this idea that the solar system started hot, everything's in the vapor state, cooled down, and different minerals condensed according to a condensation sequence. All right, that's wrong, as I will show today. It needs to be, there's much more different effects have to occur. So this is one view. Another view is that some fraction, or perhaps all, of the interstellar materials are preserved. It's less violent. And there you do have a problem. You can't get to some aspects of the meteoritic inventory. So clearly it has to be some mixture of these 2 viewpoints, but they do provide 2 extremes. All right, so what about disks? So we observe protoplanetary disks. So these are disks seen in silhouette against the backdrop of the Orion Nebula. They're called proclids, which is a term that I always hated. So they're protoplanetary disks. So this dark spot is the disk itself. Their typical sizes are on the order of a few hundred AU, but we have to recognize that that may be a selection effect, that it's easier to see the bigger things than it is to see the smaller ones. Right? So when ALMA comes on and gets many surveys, we'll have a much better idea of the distribution. The disk mass is typically 10 to the minus 2 solar masses, but I'll talk a little bit about the mass and its uncertainties. And again, the disk is mostly molecular hydrogen. All right? The disks are flared. That is, the outer parts of the disk further away from the star have a higher height than the stuff near the star. And this is actually just a consequence of gravity and thermal physics. So here is a silhouette disk. This is the flared surface, like here. Okay, stuff further away from the star has a higher height. It intercepts more radiation than it otherwise would if it's flat. Right? If it were flat, it wouldn't capture as much radiation. And what you're seeing here, this is the scattered light off the surface of the disk. So light coming from the star, hitting a dust grain, and gets scattered actually in a direction towards us. So all this stuff is scattered starlight, right, in all these systems. So this is one of the nicer. This is the butterfly. Right, you can see it, this beautiful flared star. So the star is in the center here. You see this maybe kinked a little bit towards us, maybe this way. So that's why we're seeing a little bit of starlight brighter there. Okay, so disks are flared. Disks have structure. This is quite the industry these days. And this is a beautiful picture from what's called the SEEDS collaboration on Subaru of one disk where they're seeing spiral density waves. And that's telling you something about what might be going on there. Maybe planets are being born that are exciting these spiral density waves and other things. So this is, there's lots of teams out there, the big telescopes, trying to obtain images like this. It's real beautiful work. They certainly do have protoplanets in them, but we may actually, in some cases, be seeing them. So this is from Sasha Kwan's towards one system, and this is in the infrared, and then they see this blob here, all right? And this is the disk seen in scattered light with Hubble, all right? And this is where they're seeing their potential protoplanet candidate. And what's going on is that, the idea at least, is that when a planet is forming, it's accreting material from the surrounding disk. It's releasing that energy, and the claim is that might be what we're observing here. So that's kind of cool.
So that,
Yeah.
the scale there is just intensity, or is it somehow it relates to temperature of the...
Intensity. Yeah, so this actually is polarization. They do this through polarized images. So this is intensity, this is probably polarized. So it's nothing to do with the temperature. Yeah, we don't have, I don't think, to my knowledge, well, as of 2013, they didn't have a spectrum, more than one wavelength towards this thing. So what you'd like to do is, yes, observe it, see if you can fit it with a black body, determine its temperature, and so on. There's other candidates out there. Okay, so the young planet accretes material from the disk, releases energy. Of course, the dominant thing going on here is that the material is being fed from the disk onto the star. And so this is the closest star, TW Hydra, which is about 55 parsecs away. It's the closest star with the disk system, and it is accreting material from the star, or from the disk. It's falling onto the star. So this is the emission from the star right here. Okay, and there's this excess to the ultraviolet. All right, so there's energy coming out from this accretion that is being released and hitting the disk as well. So there's molecule-destroying ultraviolet radiation. But this is another industry where you can measure the mass accretion rates. In a way, even if you didn't know a disk is there, if you detect this excess, you actually have inference that there's a disk present. Disks are also, or young stars, misspelled there, are 1,000 times brighter in X-rays than our sun, actually. So they're actually X-ray, energetic X-ray sources. So this is it's called a Christmas tree. This is an image of the Orion Nebula, but now in X-rays. And every point source you see there is a young star that's being born in this cloud. X-rays are an excellent way to find young stars. So Feigelson and Getman, there's a beautiful work by that team there. So they're typically 1 to 2 keV X-rays, but they do extend to higher energies. So that means, we have the star is emitting X-rays, it's emitting ultraviolet, so the disk its surface is exposed to energetic radiation. So the ionization environment is such that, this is from my student Ilse Cleaves. This is a schematic of a disk. This is height, this is radius, this is the ionization rate from X-rays, or the X-ray flux, not the ionization rate, and the UV photoflux. And the X-rays have greater penetrating power than ultraviolet photons. Ultraviolet photons are sort of hit on a skin depth of the surface. X-rays can go a little bit deeper. Why is that? Well, the ultraviolet photons see the grain, which is has a cross section of about 0.1 microns, pi 0.1 microns over 2 squared. Right? The X-rays, however, see the atoms, even the atoms in the grain. So you're talking about an angstrom size scale. So they can go a little bit deeper into the disk. And so actually this is decaying very rapidly, whereas this is not. So both of these things can foster a very active, what we call kinetic chemistry on the surface, and I'll explain that a little bit later. All right. We have our star, we have the disk. Most of the starlight is coming out in the visible. That's what's heating the disk. All right. So there is a surface where this radiation is being deposited. That surface clearly will be hotter, right, where the energy is being deposited, than the midplane. So you have a hot surface, cold midplane, and then of course it gets hotter as you get closer to the star as well. But you have two thermal gradients, right? You have a horizontal one, or a radial one, towards the star, and a vertical one from the midplane up. So that's important, okay? Now this energy that's intercepted, it's reprocessed, and it's re-emitted in the infrared, okay? And in the infrared, the warmer material emits in the near to mid-IR, so stuff close to the star emits there, and the colder material is more distant, that emits actually at different wavelengths. So this is a way, this reprocessed radiation is a way of inferring the presence of the disk, again, even if you don't have a picture of it. So this is, again, another industry. This is what's called the spectral energy distribution, where you observe if you can, the entire spectrum of the star from basically the visible all the way out to the millimeter and submillimeter. So Nuria Calvet at my institution, there's Paula D'Alessio, the late great Paula D'Alessio from Mexico, Dolomon, Chang and Goldreich, a whole bunch of groups that do this stuff. All right. So here's our star. This is the stellar black body. So now this is in frequency space. Okay, and this stuff here, this emission here, is actually the surface. That's actually coming out at the mid-infrared. That's the hot surface. And this is the colder interior. And that's coming out at longer wavelengths. So we have the star here. There's an excess. So this is what the star is emitting. And if you can see, if you observe your star in the visible, if you can detect it, you can figure out what its emissions are and what its spectrum, where its spectrum is. And if you see an excess above what the black body expects, that tells you that there's a disk there that's taking that stellar radiation and re-emitting it. So what you can do now is you can try to get at the timescales of planet formation and the timescales of disk evolution. All right, and so people look at clusters where they can estimate from the cluster what the age is, and ask what is the fraction of disks that have an excess emission, or fraction of stars that have excess emission in the infrared, i.e. they have a disk. So this is the disk frequency versus the age, and you see that there's a fall off. All right, so this says that timescales are on the order of about a few million years. Now, what is this important? This is actually the dust that's doing this, and we're inferring that the evolutionary timescale for the dust and the gas are comparable. Almost going to tell us whether that's true or not. But at face value, this tells you that you have to make gas giants while there is a gaseous disk present. So this says you have to make the gas giants in a few million years. Now, there's been some recent work changing that has looked at the cluster ages and actually shifted them by a factor of 2. This is by Bell et al. 2013. So, whereas before we had, whatever, 2 to 3 million years, and the theorists like Jack had to go out and figure out how to make giant planets in 2 to 3 million years, everything is now shifted by a factor of 2. In this direction, according to this analysis. And if that's the case, you still have a gaseous disk all the way out to sort of 5, 6, 7 million years. Okay, so the other thing you could do with the models of the spectral energy distribution is construct a physical structure of the disk. That is, what is the distribution, the radial and vertical distribution of the density, and the radial and vertical distribution of the temperature. So here is, again, TW Hydra, now in wavelength land. There's the star. Here's my infrared excess. There's a disk present here. And this is a model. This other line is a model of the disk. The points are all the data points that we have. Here's the system. All right, and so this is an example from Nuria Calvet and D'Alessio. You can have, this is vertical height, radial height, and these lines here are the temperature. So hotter on the surface and hotter when you get closer to the star. Here's the 20K, so it's very cold in the outer parts of this, and this is the density. So 10 to the 9, 10 to the 8, 10 to the 7, 10 to the 6 per centimeter cube. It can get very dense. This stops here at 40 AU. You can get very dense at that and much higher pressures at 1 AU. Okay. Now, so there's a trick here, right? That you're doing very detailed radiation transfer. You're taking the star is emitting, it's being absorbed by, the energy is being absorbed by dust grains and then re-emitted in the infrared. So you need to have an understanding of the dust, how the dust is taking that radiation and re-emitting it. But we have a little problem here. Your disk is making planets. Your dust is growing, all right? So if you start with your typical grain of points, so the whole disk is 0.1 micron dust grains, although probably actually more dust grains that are smaller than 0.1 microns, and they're getting together making bigger and bigger things. So your response to radiation, the optical properties actually depend upon the grain size. So the process of planet formation actually is tied into how to extract and understand emission. So here's another example of the dust, and then I'll show you a little bit about the optical properties. So this is from the SMA. These are a handful of disks from Sean Andrews, where they have the millimeter, sub-millimeter continuum emission. So when you're out here, this emission here is optically thick, so you're only probing the surface of the disk. Out here, the emission is optically thin, you're probing the mass. So he can estimate the mass of the dust in this from the emission and assume some relationship between the dust and gas mass to get the total mass of the system. So you have the flux, the distance, and this property here, this one magical number here that converts this emission, saying, okay, this much emission is coming from X mass of dust grains plus X mass of gas, and then the temperature structure, which is a black body. So the mass is proportional to the flux divided by this, what's called the mass opacity and the temperature. Okay, so what are we after here? The framework, the idea is to actually look at our solar system and ask, well, this is the way people do this at least, is how much mass do we need to create the solar system? So Jack talked about this briefly. It's called the minimum mass solar nebula. And so what people have done, and so Hayashi did it in 1981, Whiting-Schilling in 1997, and they asked how much mass do you need to make our solar system? It's on the order of about 0.01 solar masses. This is the mass distribution that Hayashi obtained. And just to show you how this is done, this is mass per centimeter cubed, the surface density of mass, and this is radius. What you do is you take the planets, you grind them up into pieces, and divide by some delta R here. And these are the solid planets, terrestrial worlds. This is Jupiter. That's the estimate of its core. There's its envelope. All right, and so this is the surface density of solids in the solar system, and then you assume that there's a factor of 100 more gas, and that gives you this line. Why a factor of 100? Because by mass in the interstellar medium, there's 100 times more mass in the gas than dust. So that's how you estimate. So we know the terrestrial worlds had this much solid, so there must have been more gas here, right? That went away, dissipated, didn't make it into the planets. Really, Jupiter's the one that tells you what's going on. All right, so that's about 0.01 solar masses. So that's what we're trying to look at here. Do these disks have comparable masses? So this is quite the plot here, but it'll give you an idea. So the emission here, the opacity of the dust grains is proportional to this kappa times the mass column density. How much mass of grains are there? Now, what Drain did is he took models of the optical properties and took a distribution of grain sizes and said, well, if I change the maximum grain size by a factor of 10, another factor of 10. So here we go. When grains are, let's see, we have grains at 10 micron in size right here. Okay, and then you could have grains that grow to 10 centimeters in size. And this is versus wavelength. So things are changing here. And in fact, you can see this wide distribution is almost over about factors of 20 to 50. All right, so what that says is that when grains grow, this magic number that you're using to calculate the mass from is changing. And you need to have some understanding of how grains are growing. Yes?
There's a brief question. In the previous slide,
Mhm.
what, previous to that, what makes people think that the ratio, this factor of 100, would be the same for radially from the star, when the disk itself has huge differences in its structure?
We just assume it because we don't know any better. We don't have any other information. So Renato's asking, why is this magic factor of 100 the same everywhere? It probably should vary, and indeed it should. And some models actually do include some variation in it, but it's not very well constrained observationally. We have one system that I'll show you where we have an estimate of the gas mass independently. One. All right, so the dust grains are a moving target. If the dust grains have grown to a meter size, we're observing in the submillimeter. So we see grains that are typically on the order of submillimeter sizes. That's what predominantly emits at those wavelengths. If grains have grown, if you've made meter-sized bodies or kilometer-sized bodies, they don't emit at wavelengths that we can observe. We do not know that they are present. All right, we are only sensitive to things at the size that we observe. So that's an interesting statement, right? So here's what is done. This is the mass, again, per centimeter squared versus radius. This is from Williams and Cieza, but it's really from Sean Andrews' work. This is the solar system, the minimum mass solar nebula with some sort of error bars. And this is the radial distribution of dust that we're observing. And you can see it's comparable to what the solar system is. Some of them are higher. But our resolution limits, actually, as you can't see it very well here, it's here. So this data point is actually meaningless on this plot. Everything is set by Uranus and Neptune. And we haven't even gotten to Jupiter, right, which is our best data point, because it has most of the mass in the planetary system. So ALMA's going to do a lot better than this. But again, if grains have grown, and perhaps they've grown radially, that is, there's bigger grains near 1 AU than there are near 30 AU, then our plots, this plot here, could go in either direction. All right, this distribution. So that's a limit where that's just astronomy you have to live with. Now we do have one system, thankfully. With Herschel, I was able to obtain this spectrum from hydrogen deuteride. I was very happy when it came, when that detection showed up. I had a survey about 6 sources. This is the only detection. 1, maybe 3 sigma. This is it. So this is an isotope of isotopolog of H2. So it's basically H2. It's going to follow H2 in the gas. It's 1,000,000 times more emissive than H2 itself at typical disk temperatures. And I know the D to H ratio. That is, if I observe this, I know how to convert this to an H2 mass. And what I find is that the typical mass of the system is on the order of about 0.03 or 0.04 or 0.05 solar masses. And so this is the system where we actually, the one system where we actually have a mass estimate. It's comparable to what you would get from the dust. So that's encouraging, right? But we need more information. So this is the distribution that we infer by fitting the spectral energy distribution and the gas emission. So here is the density structure. So it's denser in the midplane, less dense as you go up and out. And here is the gas temperatures that we're inferring. This is from Uma Gorty's work that we adopted. So hot, hundreds of Kelvin, the surface, closer to the star, and very cold, tens of Kelvin further from. And so everything's sort of coming together as some sort of consistency. These other things are, this is where HD is emitting in our model. All right, we didn't, this spectrum is unresolved. It's all the disk is showing up in one spectrum. So this is all inference. Okay. what am I saying here? Just to summarize, the dust evolutionary timescale is only about 5 million years. The disk mass is generally estimated from the dust. In fact, all of our theories are underpinned by the dust, but it's uncertain at present. But it's really, I mean, this is going to, ALMA's really going to help us. This is going to be known soon. The best gas mass ratio is hydrogen deuteride, but this emits in the far infrared. Herschel died before I could try to get other data. So we need another far infrared observatory that can detect this line. Maybe we can use CO, but as you'll see later, there's a problem with that. That's how we get the mass elsewhere. Now, the temperatures that we see when we model the spectral energy distributions are not hot enough to evaporate the solids like we see in the solar system. So there's this inference, again, in the solar system, if we look at the rocks, that everything started out hot and cooled down. That's the so-called the model that we showed from Lewis. And this is a big thing people talk about. We don't see those temperatures. It only gets hot enough to evaporate solids inside of about 0.1 AU. That's a tiny part of the disk. All of the mass of the disk is elsewhere. So we don't see that. That's interesting, right? Now we can get resolved images. This is with the SMA, and with ALMA we'll be getting many more of these. And this is CO from Hughes et al. And you see this, what this is, this is a disk. It's rotating. The molecular line is bearing information on that rotation. And it's blue shifted and then red shifted. And if you model this, this is essentially consistent with Keplerian rotation, as in our solar system. So we're observing, this tells you that this is a disk. All right, so there's lots of things going on in a disk, and I could spend days just on trying to understand this one plot. This is from Henning and Semenov. You have your star. It's accreting matter from the disk, we think along magnetic field lines. UV and X-ray and radiation are emitted from the star. The UV is coming from the accretion. The X-rays are partially coming from the accretion, but they also have an active chromosphere. And that is hitting the surface of the disk. So the surface of the disk is what we call photon dominated. All right, so if the photons are powering chemistry, there might be a more active chemistry on the surface than there is on the midplane. All right, it's ice. It's colder out here in the midplane and deeper in the disk. So ices are present here, but it gets warm enough so that you can actually have molecules present in the gas phase, sort of in this layer, a surface layer. All right, so we can say this is carbon monoxide, say, right? It would look like this. And then you would get to an evaporation front. So here it's greater than 20 K on the surface, and here it would be greater than 20 K in the midplane. So you have your so-called frost line, but you can also have surface layers. So there's two evaporation fronts now. Remember I told you there's two temperature gradients? So we always talk about the frost line as this radial point, or the snow line, this radial point where things are evaporating. Well, there's a vertical point as well. And observationally, we see the surface more than we see the midplane. So that's something we have to think about. Now over here, the dust is settling. So the first stage in planet formation is the dust settling to what becomes a dust-rich midplane relative to the gas. All right, and that's going to change how the disk interacts with optical radiation, ultraviolet radiation. There's turbulence, things moving around. And of course, eventually, you're making planets, and that's going to alter the disk. So it's a very complicated system. But again, the complexity is a challenge. But it also means that there's lots of things that can be done and be learned for many, many years. So careers. So the general expectations for the chemistry that we talked about, others talked about as well, is you might have, say, a water snow line. So here the temperature is, say 150 K. It's ice out here and gas out here. But we now know that there's another snow line here on the surface, right, going up. We focus on water. there are other volatiles. So there might be other frost lines as well. So there could be a water frost line, there might be a CO2 frost line, there might be a CO frost line. And I'll show you that we have evidence for that. So different ices could be evaporating at different points in the disk. Now, observationally, we can observe many of these things, and this is a beautiful spectrum of one disk from the Spitzer Space Telescope, where we see all these lines, all these things that are labeled here are water. That's water emitting from this one disk. There's also HCN, C2H2, CO2. There's an H2 line here and a recombination line of hydrogen. This is on top of it at all. Now, this water is not actually due to ice evaporation. There's another problem with water. So I showed you the way that you make water in cold gas yesterday. So you can make water in hot gas by evaporation, but you can also make it from reactions of oxygen with H2, which goes to OH, and OH reacts with H2, and that goes to water. And this is when the gas gets hot. We're about 400 K, a little bit lower. And this is very, very efficient. So just to show you that, this is the water abundance versus time for fairly high density and different gas temperatures. So 100 K, the water abundance is low. 150 K, it starts rising. You get to 200 K, and in about 10 to the 5th years, you have a very high abundance at 300 K there. And then if you ever get to 1,000 K, I call it a water bomb. Just boom, all of a sudden you have water in the disk. Now this chemistry is not what we talked about before, and what Jack was talking about, this so-called quote-unquote equilibrium chemistry. Equilibrium chemistry, the best way to explain that is it's the chemistry that will happen that all things would tend to if you waited forever and a day. All right, now why is that? Because reactions have different time scales. So if you could wait forever, you would get to the time scales where all reactions had occurred. But some things happen quicker, some things happen slower. This is called kinetic chemistry. And if something's happening slower, you know, if some reaction time scale is, say, 10 to the 7th years, and my disk only lives for 10 to the 6th years, I don't reach equilibrium in the chemistry. This is an example of a reaction that's temperature dependent, that may not reach equilibrium depending upon the temperature. So here is an example of what the water distribution then looks like that actually matches or comes close to matching some of the observations that we have. This is from my postdoc, Bujun Du, and it's based upon work by Coco Zhang at Caltech. So this is the disk, this is height and radius. We're only seeing water basically right next to the star where it's hot enough for one, to evaporate water, and for two, for that active chemistry to occur. And very little is happening actually. There's the surface layer. Here's 1,000 K, there's the photon field is too high for you actually to make water. And then there's a very tenuous amount of water as you go out. Here's another example. So here what we're doing is we're varying the amount of gas relative to the dust. Let's say that the dust grains are evolving, all right, and you're on your way to making planets. What happens to the water? Well, as you get on your way to making planets, the dust grains get bigger. What does that happen? That means the disk becomes more permissive to radiation, and you actually destroy the water. That's what's shown here. So this is a higher dust to gas ratio, and as you get to less dust relative to the gas, you get less water. Okay, so another example of the fact that we actually have active chemistry in the system came from carbon monoxide in TW Hydra. Now, carbon monoxide is something that we'd like to use to trace the mass of the disk. In the ISM, we know the abundance of carbon monoxide is calibrated. It's about 10 to the minus 4 relative to H2. So if I observe some optically thin CO emission, I can add up its mass and get the CO mass of that cloud and divide it by 10 to the minus 4, and voila, I have my mass of that object in hydrogen. When I told you that the typical mass of clouds that are going to make, or cores that are going to make the sun, is only order, say, a few to 10 solar masses, we observed that in CO, and we took that CO abundance and estimated its mass. So we'd like to, instead of using the dust, we'd like to use CO in the disk the same way. So what we did is we took our emission from HD, which traces H2, and we had an observation from the SMA of C18O. And the flux ratio should be proportional to the CO abundance. And when we do that, we found the CO abundance is less than 10 to the minus 5. And this is not due to the fact that the CO is frozen as ice is, actually, because both of them are probing. Both things are only emitting from this sort of surface layer here. So this is radius and height, and we're probing the abundance right in this gas here. And there's technical reasons that I could use to explain that, but the upshot is something is destroying CO in this disk. All right, so where is it? What is it? What we think is going on is that there's X-rays. So this is a plot now of the ionization rate, again from Ilse-Cleves. This region is X-ray dominated. This region may or may not be cosmic ray dominated, but just the parts where there's X-rays. This is actually not the flux of X-rays. This is the ionization rate of helium. Helium is a noble gas. It does not freeze onto the surface of grains. It is in the gas. X-rays are present in the system. They will ionize helium. Helium will then react with other molecules, and actually it can destroy CO. So here is an example of a model. Here's our disk. It's flared. This is freeze out. This is where CO is frozen. The CO abundance here in blue is the normal 10 to the minus 4 abundance. But this layer here is where helium is destroying CO. And as time goes on, it takes away more and more of the CO. Where does it go? It goes into organics. It goes all over the place. So this is the fraction of carbon held by anything. This is versus radial height at 10 AU. And we're making HC3N, C4H2, all kinds of things. All right. The key point here is that there is an active chemistry, and it's happening everywhere. All right. And this chemistry is not in equilibrium. Observationally, we can also probe the outer disk, and this was done in a very nice survey by Karen Oberg with the SMA, and again with ALMA, we're going to get a lot more of this. So these are all different spectral lines detected towards a bunch of disks. There's lower mass stars than the sun. Actually, when stars like the sun are young, they masquerade as what's called the spectral K stars. So stars like the sun are in here. So here are M stars and K stars. This shows that we're seeing disks. This is the rotation. And we observe things like, well, let's see, this is CN, this is DCN, not detected, HCN detected, formaldehyde detected in a couple of systems, N2H plus detected in a bunch of systems, DCO plus. So DCO plus says that cold chemistries happen, HCO plus, CO. All right, we're seeing the surface here. That's an important point. We're not getting to the midplane. The molecular abundance, if we look at them, they're lower than we see in cores, and we think that that's probably due to formation of ices. But there's an active chemistry. Now, we don't see the most complex organics we see really is formaldehyde, C2H2, HCN. So we're not at that point yet. Now, we also included some stars more massive than the sun in this survey. And the one thing we found is that stars that are less massive than the sun have more molecules that are what we call cold emitters, things like N2H plus and so on. And what that is it's just pretty simple. At least our understanding of that is that if you have a star like our sun, what happens is, so N2H plus emits where CO is not. So N2H plus plus CO is this is the main destruction pathway, and if you don't have CO, if CO freezes out in the gas, then the abundance of N2H plus picks up. So here this would be the CO frost line in the midplane or on the surface. Okay, this is where N2H plus would be, and this is where CO would be. And if you have stars that are more massive than our sun, what does that mean? It means there's more heat, and that means the midplane is hotter. CO is now present here, and N2H plus is not. So again, evidence for active chemistry. Okay, so I've given you 3 examples of active chemistry in the disk based upon observations and models. This chemistry is not in equilibrium, so it's ruled by kinetics. So we have to move beyond the Lewis model. We are not yet probing the midplane. N2H plus is probably the closest we're getting to the midplane right now. But and the other thing is that when we look at our chemical models, we don't see the equilibrium solution except for perhaps inside about 0.1 AU close to the star. So if we see this evidence from the meteorites that some things were evaporated and reformed, when did that happen? Right? We're looking in disks where we think this happened, and the only answer can be during disk formation. That there has to be some phase that was very violent where some fraction of the solids basically were vaporized and then reformed. And that was T equals 0 that we're seeing in the solar system. And so here is an example of where that might be. This is the bolometric luminosity, or just the luminosity of a bunch of protostars. So these are the stars with disks, and these are protostars. So here, this is the phase where the disk is forming. These objects all have very comparable temperatures, but their luminosity ranges from basically 0.1 all the way up to 100. So that's 4 orders of magnitude in luminosity for an object that has a star that's about the same mass. How the heck can that be? Well, that can be because this is not energy from the star, this is energy from accretion. And maybe what you have up here is an event, an accretion event that is variable, where you dump a lot of material in the star, release a lot of energy, you blow away some solids, they reform, and then it goes back down again, and it goes up and down, up and down. So that's the current idea about how the stars are born. They're born via episodic events of accretion, and that would be happening when the disk is forming and may influence the chemistry in some ways. All right. Now with ALMA, we're going to be doing some really, really cool stuff, and this is an example of one of the really cool stuff. It's called chemical imaging. So this is from data from Charlie Chi. And so I just showed you here that we believe that at the CO snow line, where CO frosts out, all of a sudden N2H plus can be allowed to form. So here's the CO emission towards, this is TW Hydra. Here's N2H plus. We see a hole in its emission. And we argue in this paper that this is the CO snow line. And we can see it with sort of a negative image. All right, now why can't we see it in CO? Because CO is emitting both from the midplane and is also emitting from the surface. Right? So it's hidden. It's basically hidden. You would never see it in CO. But you can see it in this thing, which is a negative image. So we might be able to get the water snow line in the same way, using some reactive ion. Why is this neat? Well, because it may tell us where Jupiter was born. This kind of stuff. So what is that? How can we make that argument? So here, if you have a disk, you have a thermal gradient. Okay? You can have a CO snow line, a CO2 snow line, a water snow line. All right? So, if I'm inside the water snow line, everything is in the gas. All of my carbon, all of my oxygen. So my C to O ratio here will have the C to O ratio that's the same as the sun. The C to O ratio is the total amount of carbon, adding up all the carries of carbon. And here The oxygen is all the carriers of oxygen. Now, in this example that I'm going to show you, the carrier of oxygen is CO2, CO, and water, and the carriers of carbon are CO and CO2. Okay, so now I've marched inside the water frost line. Water is in the solid state, but CO and CO2 are in the gas. So my C to O ratio would be 2/3, and the ice ratio of C to O will be less than the salt. Why is this interesting? If you form a planet right there, and this is where it accretes most of its envelope, its C to O ratio would be that. Okay, now let's go in the CO2 snow line. Here we go. CO's in the gas, water and CO2 in the ice. The gas phase C to O ratio will be 1 because it's C and O. That's it. And the ice C to O ratio would again be less than solar. And if you form a planet out beyond the C to O ratio, everything's in the ice. So you don't get as much unless you evaporate things. Okay. So there are claims now from exoplanet folks that they can estimate the C to O ratio in hot planetary atmospheres. So here's from Niku Madhusudan. There's also Johnson and Moses and others. So here's a C to O ratio of 3. This is the planetary spectrum predicted versus wavelength. And if you can see, it's different than if the C to O ratio was 0.4. Okay? So we might be able to determine, if, we know that planets can move in the disk, maybe we can track back where they were born. Now, this is kind of neat because in our own solar system, we might be able to tell where Jupiter was born if we can measure its C to O ratio. We actually know the carbon content of Jupiter, but the oxygen abundance of Jupiter is uncertain. Why is that? Well, we sent a probe in from Galileo to actually measure the amount of oxygen that's in Jupiter. It's going to be in water, but it didn't see any water. And so the idea was, well, the probe was in a dry spot. Well, maybe. Or maybe the C to O ratio is not solar, and we don't know where, and there's less oxygen in Jupiter. So Juno's going to go to Jupiter. It'll get there in August 2016, and it's going to make this very interesting measurement. So for example, this is the predicted C to O ratio for Jupiter from Moises. This is what's measured. You could go up there, and we don't know what it's going to be. This is the carbon. You can't see that. But we'll be able to, hopefully, with Juno, measure the C to O ratio, see if it's solar, see if it's not solar. And maybe we'll be able to tell if Jupiter stayed at where it is now for its evolution, for when it was born. Okay, so that's kind of neat. So with ALMA, we're going to be tracking volatiles all the way throughout, and we may be able to relate them to exoplanetary atmospheres, in addition to relating things to our solar system. Right? So we relate to our solar system. We now know that things are colder in the disk than what you come up with if you just look at solar system bodies. Okay, we learned something. Now we have to take that information and understand how we got the stuff we see in the solar system. And we now know that there should be gradients in the disk, that we should be able to measure both with ALMA and calibrate this C to O ratio business, and then correlate that to exoplanetary atmosphere. Now what about making the Earth? And I think I wanted to show a little bit of this because no one's talked about this yet. If you want to talk about dust growth, I just have a few slides on this. It's not an area where I'm a major expert, but it's important. So this is the optical and infrared. You have your grains here. They're born here, so 0.1 microns. You got to go all the way up here to thousands of kilometers. All right, and here's the Earth, right? So how many orders of magnitude, right? We're talking huge amounts of order of magnitude from the beginning to this wonderful rock that we all know and love. We can probe observationally this part in the optical and infrared. We can probe this part of evolution up to about centimeter size, maybe decameter sizes. with our telescopes. But then we can't probe that. All right, so this is in the area where there are models. All right, and Leonardo Testi says, "Here be dragons," right? Because this is all due to the problem. Now the models say that actually in this growth process, so actually up here we have some reasonable idea of the evolution, and that's what Jack talked about. But below that, there are two barriers that need to be understood and overcome. One's the so-called centimeter barrier, and the other is the meter barrier. The centimeter barrier is due to collisions. The meter barrier is due to differential drift. So what is that? If this is a plot, this is from Wimmark et al., showing if you have grains of this size colliding with grains of this size, what happens to them? That is, if they're on the order of about 1 centimeter inside, they may bounce, or you may transfer mass. That means they're going to grow. That's good. But when you get big things colliding with big things, they break apart or erode. So this is the so-called centimeter size barrier. This has to be overcome, and it clearly was, or we wouldn't be here. Otherwise, disk would be just filled with pebbles, and we would never make anything bigger than pebbles. But this is a barrier that theory suggests has to be overcome. And there are some ideas that you might have. Instead, this is make some assumptions about grain velocities, maybe if there's a distribution of grain velocities. So only the slower things happen, and then you actually shift things down into this area where you're either going to stick or you're going to get mass transfer. And you may actually be able to overcome this that way. The meter size barrier is another problem. Okay, and Jack talked about this. The way this works is that the gas is orbiting more slowly than the solids at a given radius, right? And that gives a headwind that causes particles to drift inwards. And the velocity depends upon the size. The small grains, much less than 1 centimeter, are coupled to the gas. The meter-sized particles are the ones that most rapidly drift, and the large planetesimals just sit there. Okay, so this is from Cousy and Zonley. This is the drift speed versus particle radius, and you see it peaks around 1 meter and then drops off. We see this. We observationally see this. There is a difference between the emission radius of the millimeter-sized grains and the smaller grains, the centimeter-sized grains as well. So we know this is happening. Now, the meter-sized particles, or if you can get to meter size, they would just go right into the star. You have to stop this. This has to be overcome, or again, we wouldn't be here. So how do you do this? Well, the idea was, and many people have taught about it, or talked about it, is that you can have some sort of disturbance in the disk that gives you trapping mechanisms, perhaps a vortice or some sort of turbulent, again, vortex that's going around, and that would collect the dust locally and allow them to just sit there and grow. And with ALMA, there have been 2 papers, Van der Merel and Cassusis, where we now have detected these so-called dust traps. And they can often be asymmetric. So what this is the millimeter emission towards one system, and you see this sort of peanut-shaped. The micron-sized grains are radially distributed all throughout this. But the millimeter-sized grains are all here. They're not over here, they're not over here, they went here. They're trapped here in a dust trap. And this is likely how you're overcoming the meter size barrier. And it's basically a factory where you're going to probably, I guess, make the next planet. So this is a big deal. And one of the big things, the other big things that came out of some of the ALMA first results. So this is an idea of what that would look like. So you have smaller grains all throughout the disk, but the bigger things are collecting in this vortex. Okay. To summarize the disk stuff, I'll then briefly go to solar system. I'm going to talk more about this tomorrow when I try to make an Earth. The molecular emission traces the velocity field very nicely. You can get the Keplerian. We have indirect evidence for evaporation fronts. Our chemistry is not in equilibrium, and I presented many lines of evidence that we have an active chemistry, and that's great. We got this billion-dollar instrument that we just built. We're going to be able to do lots of really fun science with it. We've detected dust traps, and we don't see right now the phase that appears to be imprinted in meteorites. All right, solar system, again, my favorite picture. Jack talked about this. We don't need to go there. I'm going to look at meteorites real quickly. Here's an example of one. If you look at meteorites, in particular the most primitive ones, the so-called carbonaceous chondrites, and if you make a plot of the abundance in chondrites versus the abundance in the solar photosphere, you find that they are identical. Ain't that cool, right? So the primitive rocks, here we go, are the same as the sun. Now there are some divergences. Well, let's see, what are those divergences? Well, let's see, these are all noble gases. They're in the solar photosphere, but they're not in the rocks. Okay, well, we know why that is. Noble gases don't react. They don't go into rocks. That's kind of cool. Okay. Carbon and nitrogen, they're volatiles, actually. They're harder to get into rocks. Again, in the sun, not in the rocks. Hydrogen, same deal. Okay, well, here's one that is present in the rocks, but not present in the sun. That's lithium. Well, the sun, when it's young, destroys lithium, actually. So this one makes sense, too. Now, this trend is so cool and so neat that if we cannot observe an element in the sun, we can estimate its abundance from the rocks. All right, so some meteorites actually come from Mars and the Moon. Most of them are from the asteroid belt. Most of them are part of big things. Some of them are differentiated. We talked about that. David talked about that. Where the heat has melted the material, and so things sink to the center. Where did the heat come from? Where did they get the heat? Anybody know?
What question?
Where do they get the heat to differentiate meteorites?
Radioactivity.
Radioactivity, right? So 26 aluminum is what's doing it. All right? So 26 aluminum is providing the heat that melts them. Now, there are models or questions about where the 26 aluminum came from. The sun, we don't think, can make it. So it had to come from some external source. It's made readily in supernova. It's made in the winds of stars, Wolf-Rayet stars and other stars. And so there was a very long history of trying to understand where the 26 aluminum came from and whether we're an oddball in that regard. Now there's lots of observations, and modern thought seems to think that it's very common for systems to be born with 26 aluminum because there's supernova and all kinds of other things happening in interstellar medium. So that's kind of cool, actually, because as you'll see, the 26 aluminum is crucial, actually, to making the organics that we see in meteorites. And if 26 aluminum was not common everywhere, then there might be different results for the meteorites. Okay, so most meteorites are from undifferentiated parent bodies, all right? And they have, what are called chondrules, which are little spherules. There's also some sort of matrix or cement that's between these chondrules, and then these calcium aluminum-rich inclusions, which are the oldest material in the solar system. So here are the chondrules. See these dark things, and then all the stuff in between them is the matrix. And here we go, another example. So this is calcium aluminum inclusion right here. The rest are chondrules, and then the dark stuff, that's the matrix. Okay, so chondrites are named after the most abundant constituents, which are chondrules. There's two flavors, ordinary, these are the most abundant ones, and the carbonaceous ones, these are less abundant, and they actually have a bigger amount of matrix. Okay, now as David mentioned, these things have water in them. Okay, and in fact, that water was liquid at one point, leading to an aqueous chemistry inside the asteroid that took whatever the primitive stuff that was implanted in those rocks and made more complex molecules. That's interesting. And this is due, again, to 26 aluminum. So you need to have liquids, you need to have that heat. All right, well, talked about CAIs, first solids, oldest things. Okay, now, what about organics? So in the Murchison meteorite alone, all right, about 1.5 to 4% of carbon is in the matrix. 70% of the carbon is in the form of some sort of macromolecular material, some sort of insoluble. So it wasn't the part exposed to aqueous material, but it's still got hundreds of carbonations, carbon atoms in this sort of macroscopic stuff. And 30% of the carbon is in the soluble part, in the part that's exposed to aqueous chemistry, or was exposed. And they detected over 1,000 molecular species, 100 amino acids, all of the terrestrial kinds, plus a lot of other things. And it's probably some sort of liquid initiation chemistry from something simpler. And a sample of 12 meteorites finds nucleobases as well. Now, the carbon content of meteorites, as Jack noted, and I'll talk about this a little bit tomorrow, here's the carbon content. This is relative to silicon. These are meteorites. Here's comets. Here's the Earth. Here's the Sun. So this was what was available to make the carbon that we see in meteorites when they were born. There is about an order of magnitude less carbon in meteorites than was available. So carbonaceous chondrites are actually carbon poor. And this actually is a problem that I'll talk about tomorrow, and it may be a problem for making Earths. And here's the Earth. We don't know the carbon content of the Earth because there could be carbon sequestered in the Earth's core. But the mantle, that's this number here, actually no, it's this number here, is substantially carbon poor. That's kind of neat. All right, well here's an example of some of the carbon that did make it into meteorites, and the various flavors of chemistry. So there's carboxylic acids. This is acetic acid as an example, that's vinegar. We have amino acids, right, the building blocks of proteins. We've seen that. There's lactic acid, milk acid, pyruvic acid. This is citric acid, part of it, and it contributes to the cellular energy cycle. Succinic acid, part of citric acid again. Glyceric acid, derivatives part of the conversion of glucose, making ATP, so sugar alcohols. Acetaldehyde, believed to be related to hangovers. I did drink a lot of wine last night. So that must have generated this stuff. Ethylamine, or amino acids, okay. Nicotine acid, that's vitamin B3, seen in meteorites. Adenine, DNA base. Propane, you know what propane is. Naphthalene, mothballs. Isoquinoline, maybe a neurotoxin. All of this stuff from space, made billions of years ago, provided to our planet. Maybe something happened to it and was used by life. Again, we don't know. Other thing we know is that these amino acids, and this is a plot, this is the D to H ratio. This is where interstellar molecules are. They're elevated. The D to H ratio in the amino acids, or in this carbonaceous material, is also enriched. That's hinting, again, at an origin that was not made on the Earth, or not made in the rocks. To summarize meteorites, they're the carriers of water and organics. Didn't talk about the oxygen isotopes. They have a unique signature. There's complex organics in the soluble portion, and some amino acids used by life. They have a de-enrichment, maybe from the cold chemistry. And it really shows you that you can make simple monomers from abiotic chemistry. This is not biology, this is just chemistry. All right, the last thing is comets. To provide a final closure of potential contributors to understanding where the Earth came from. There's different flavors of comets. There's long period comets that are in the Oort cloud, and they actually are thought to have formed near the giant planets and have been thrown away. So they actually form closer to the sun. And the other flavor of comets, which are short period comets that are thought to come from the Kuiper belt. The Kuiper belt, of course, is beyond the orbit of Neptune. So the short period comets came from the Kuiper belt, further away. Long period comets from the Oort cloud, we believe, originated closer to the star.
Sorry, what do you mean when comets come from the Earth but are formed in the Jupiter? That there's a transformation in the
Yeah, so when Jupiter was forming itself, lots of icy bodies around interacted with them and just threw them out of the system. Yeah. And populated the Oort cloud, Uranus, Neptune as well. When comets approach the sun, these things are very icy. So meteorites are mostly rock with some water in them, a few percent water. Comets are, almost half and half, dirt and rock. They used to be called icy or snowy dirty ice balls or icy dirt balls. They're actually icy dirt balls. So they're a lot of dirt with some ice wrapped around them. The most abundant cometary volatile as it approaches the sun and evaporates is water. And we use the same kind of techniques as the interstellar medium. This is a spectrum to observe them. So you see all kinds of things. Here's HCN emitting, water, C2H2. This is in the infrared. You can get abundances of these things. We see some complex molecules, many complex molecules in the bright comets. So this is abundance relative to water. So you can see we see some complex. These are all things we also see in the interstellar medium. They also have detected glycine in the samples returned by the Stardust spacecraft. So Stardust flew past the comet, stuck out a catcher's mitt with this gel, and caught some samples, and then actually brought it back to the Earth, where we could stub it. They have a high level of isotopic fractionation in comets, so they're very highly deuterium enriched. Now Stardust, this is an example of some of the stuff that they brought back. So this is the track through which the stuff came in. All right, and they get mostly the rocks, they don't get the ices. And they found CAIs, the calcium aluminum inclusions. All right, so that tells you that however the solar system formed, the stuff, wherever this hot stuff was, it somehow made it to where the comets were born, and comets are the coldest remnants of the evolution of the solar system. So comets really do have hot and cold. The ices need, they have CO ice, that needs 20 K. CAIs to form need 1600 K. You didn't form this thing all in one place. You formed it all over the place. So things are moving around. Here's an example of a measurement where we get the D to H ratio. So this is from Hartley 2 from Herschel, Hartog et al. There's the HDO detection, H2HCO detection. And the prediction was, if you think about the way deuterium chemistry works, is that the disk is hot near the center and colder further out. Deuterium chemistry is powered when it's colder. Ergo, there should be a gradient in the D to H ratio in the nebula. Less, more as you go further away. Now, I just told you that Oort cloud comets came from near Jupiter and Saturn, so they were formed closer than the star. And Kuiper belt comets, short period comets, formed further from the star. Ergo, Kuiper belt comets, or short period comets, should have a higher D to H ratio, they formed further than the star, than Oort cloud comets. So we had measurements of the D to H ratio from Oort cloud comets, and we found that this measurement from the short period comet was a factor of 2 lower. That is not what we had expected. That was not what we had predicted. And in fact, it has the same D to H ratio as our planet. It's water. So here is a plot of that. This is what the sun is and the interstellar medium. And Jupiter, we actually have a measurement from Jupiter. This is the Earth right here. That's the Earth's water. Here's the short period comet, Kuiper belt comet. Here's the Oort cloud comets. Again, our theory was wrong. Needs to be revised. There's more understanding. Here's Enceladus, neatly. So you can measure the D to H ratio in the plume coming out from Enceladus. That's kind of neat. And here are carbonaceous chondrites. So if you want to use this as a fingerprint to tell you where the Earth got its water, well, then your candidates are asteroids and comets. And before that measurement, comets didn't play into it. But of course, things were moving around, so maybe these things are actually samples of the same kind of material. All right, so comets have cold water, ice, and organics, hot solid state refractory components. Oh, let me just, again, this just shows you. This is where, if the Earth formed, if the Earth's water came from 1 AU, this is where our D to H ratio would be. This is where it is. Okay, so again, this tells you that the Earth got water from a cold source. Okay, so we see both hot and cold. There's deuterium enrichments. and you somehow have to mix the hot and cold together. All right. So we want to make an Earth. I'm going to do that tomorrow. I'm going to try to do that tomorrow. How do these organics form? We certainly see a march towards complexity, and we think that, you know, most likely if the simple things are made in the stellar medium, they make it into the rocks as ices, and some fraction of those ices survive even in the rocks sampled in the asteroid belt. They clearly do. Water is an ice. And then the aqueous chemistry takes those simple things and probably makes more complex things in the meteorites, maybe even in the comets. I don't know if the comets could be exposed to aqueous chemistry. They might be. Our chemistry in the disk actually is informed by what we're doing in the interstellar medium. I didn't motivate that, but it's definitely kinetically dominated, not equilibrium. There must be some mixture of equilibrium chemistry that happened early and then colder stuff happened later. And David talked about how you can potentially supply things to terrestrial worlds. And what I want to talk about tomorrow is, you know, where are the sources of supply? How common is it to supply carbon? How common is it to supply nitrogen? How common is it to supply water? Now, whenever I do this stuff, I'm not going to be making DNA. We will not be making DNA. And what we want to know is, can we provide the content to the planet that the planet can then use in some way back in the depths of time to make life, and whether this content is common in planets that form all over the place. So that's it for today. Thanks a lot.